Welcome back to AI Codecast. Today, we're diving deep into a classic coding problem. It's one that's really fascinating and also super practical at the same time. And that is counting prime numbers, those numbers only divisible by 1 and themselves, that are less than a given number, we'll call it n.
Absolutely. Prime numbers, they're really foundational in number theory, and they actually have a ton of applications in the real world, especially when you think about cryptography. When you're securing your online transactions, they're using RSA encryption, and that uses prime numbers. Finding these prime numbers efficiently is a challenge that, programmers face all the time.
So, like, if you're given a number, let's just say 100, and you need to figure out how many prime numbers exist between 2 and 99, like, where would we even begin with that?
Well, the most intuitive way to do this is what we call brute force, right? It might not always be the most elegant or the fastest way, but it's really good to start there because it helps us understand the problem from the very beginning.
Okay, so let's break down this brute force method. What are the steps that we'd actually have to take?
So imagine we're just walking through each number from 2 up to n minus 1. So in our case, up to 99. For each number, we got to ask ourselves, is this a prime number?
So we're doing a primality test, basically, for each number. But how do we actually determine if a number is prime or not when we're doing this brute force thing?
So we could try and divide the number by every single number that's smaller than it. And if we can find at least one divisor that's not 1 or the number itself, then we know it's not prime.
Okay, that makes sense. But it also, sounds like it could be really computationally expensive, especially when the numbers get larger and larger.
Yeah, you're absolutely right. That's one of the biggest drawbacks of this brute force approach. Like, let's say we're checking if 97 is prime. We'd have to divide it by 2, then 3, then 4, and go all the way up to 96, potentially.
Yeah, that's a lot of division. There has to be a way to make this better, right? I mean, we are AI Codecast. We love efficiency.
You're thinking in the right direction. Think about it. Do we really need to check divisors all the way up to the number?
That's a good question. Is there some point where we can just stop and be sure it's prime? What if we just go up to half the number?
You're getting warmer, but we can actually be even more clever than that. We only need to check the divisors up to the square root of the number.
Wait, really? Why is that? I mean, it seems kind of counterintuitive. Like, why just the square root? Could you break that down a little more?
Sure. So it really comes down to how factors work. Every single number that is composite, meaning it's not a prime number, has to have at least one factor that's less than or equal to its square root. So if a number has a divisor that's bigger than its square root, then it also has to have another divisor that is smaller than its square root.
Oh, I see. So if there's a divisor bigger than the square root, we would already caught it because we checked the smaller divisors.
Exactly. So what this does is it cuts down on the number of divisions that we need to do. For example, the square root of 97 is something like 9.8, so we only need to check for divisors up to 9.
That's a lot better. So we've already made this brute force approach a lot faster. Yeah. But I still can't help but wonder if there's an even more efficient way to find all these prime numbers.
There is, and it's this technique called the Sieve of Eratosthenes. But before we jump into that, let's think about how we could actually write this brute force approach, not with actual code, but like a general idea.
Yeah, let's think about it algorithmically.
Okay, so we could start by creating a function. Let's just call it count primes. It takes our target number n as the input. And inside the function, we have this loop that goes through each number from 2 up to n1.
Okay, so that sets us up, going through each of the potential primes, and then what happens inside the loop.
So for each number, we got to check if it's prime, right? So we need another function, maybe we can call it isPrime.
Right, and that isPrime function would be doing that square root check, all that optimized stuff that we just talked about.
Yeah.
And it would return either true or false.
Exactly. So back in our count primes function, if isPrime says, hey, this number is prime, we would increase our counter, and the counter is just keeping track of how many prime numbers we found so far. Then once the loop is finished, we just return the value of our counter.
That's a really clear breakdown of the brute force approach.
Yeah.
It's really easy to understand, but it also shows how it could be really slow, even with the square root optimization, when we're dealing with those really large numbers.
You've got it. It's like, the brute force method is like using a magnifying glass to find a single grain of sand on the entire beach. It's going to work, but it's going to take a long time. There are definitely better tools out there for this.
Yeah, I'm definitely ready to hear about those more powerful tools. The Sieve of Eratosthenes, you said. Let's switch gears and uncover the secrets of this elegant algorithm in part 2 of our deep dives. Okay, so we've gone over the brute force approach, and it's A good starting point, but it's definitely not the fastest.
Yeah, it's kind of like if you were trying to climb a mountain by taking the longest, windiest trail. I mean, you'll get to the top eventually, but there's got to be a better way, right?
Right, like a shortcut.
Exactly. And that's where this Sieve of Eratosthenes comes in. It's all about finding those primes in a smarter, more strategic way.
Okay, Sieve of Eratosthenes, it sounds pretty old and complicated. Where does that name even come from?
Well, it's named after Eratosthenes, who is this Greek mathematician. He lived like way back in the 3rd century BC, a guy who was a genius. He did all sorts of things with geography, astronomy, and math, of course. And the sieve is one of his most famous contributions to number theory.
Wow, an algorithm with some serious history behind it. So how does this sieve actually work?
So picture a grid with all the numbers from 2 up to our target number in Deer. The idea is that we're going to go through and sift out all the numbers that aren't prime, so we're only left with the primes.
I'm imagining an actual sieve,
Yeah.
separating the good stuff from the rest.
Exactly. We start by assuming all the numbers are potentially prime. Then we begin with the first prime number, which is 2, right? We mark it as prime, and then we get rid of all its multiples, like 4, 6, 8, and so on. Because we know they can't be prime.
Right, so we're just like crossing off all the numbers that we know are composite because they're divisible by 2.
Yep, precisely. Then we move on to the next number that hasn't been marked yet, which would be 3. Mark it as prime and get rid of all of its multiples, 6, 9, 12, and on and on.
Got it. So we keep going to the next unmarked number, marking it as prime and getting rid of its multiples. But when do we actually stop this whole process? Do we just keep going until we get to n?
That's a really good question. And this is where the whole square root thing that we talked about earlier comes back into play. Remember, we only need to keep going until we reach the square root of n.
Oh, right. Because any number that's not prime has to have at least one factor that is less than or equal to its square root.
Exactly. So by the time we've checked all the numbers up to the square root of n, we've basically found all the possible factors. So any number that wasn't prime would have already been caught because it's divisible by one of the primes that we've already looked at.
Got it. So this sieve isn't just clever, it's actually super efficient too. Can you give us an idea of how this might look like in code? Like we don't need actual code, just, the general idea.
Sure. We could start by creating a Boolean array. Let's just call it S prime. This array would have a size of n. And we're going to set every element in the array to true at the beginning because we're going to assume that they are all prime.
Okay, so each spot in the array represents a number, and the value at that spot tells us if we think that number is prime or not.
Yeah, exactly. And then we just go through this array starting at index 2, which represents the number 2. And if the value at a particular index is true, meaning we think it's prime, then we go ahead and mark all its multiples as false.
But didn't we say that we only need to go up to the square root of n? So do we still need to mark multiples all the way up to n, even with the sieve?
You're on fire with the questions today. And the answer is no, we don't. For each prime number p, we only need to start marking its multiples from p, because any smaller multiple of p would have already been marked as false in an earlier step.
Oh, that's smart. So like if p is 5, we wouldn't need to mark 10 as false because we would have already marked it when we were dealing with the multiples of 2.
Precisely. We're basically cutting out all the unnecessary work, and that's a big reason why the sieve is so efficient. Once we've gone through all the numbers up to the square root of n, we just count how many elements in our array are still set to true, and that's our prime count.
Wow, this algorithm is pretty amazing. It's like we're setting traps for all the composite numbers, and only the prime numbers manage to get through.
Yeah, I know, right? It's a really cool example of how a systematic approach can lead to a really efficient solution.
I'm starting to get why this sieve of Eratosthenes has been around for so long. But tell me, are there any ways that we can make this even better, like optimize it even more?
Actually, there are. Remember when we talked about how we only need to check odd numbers in the brute force method? Well, we can do something similar with the sieve, too.
Oh, yeah, because except for 2, all prime numbers have to be odd. So we can basically cut the amount of work we do in half, right?
Exactly. We can just focus on the odd numbers when we're marking those multiples as false. It might seem like a small change, but it can actually make a big difference in terms of speed.
This is awesome. We started with the brute force method, then we discovered the sieve of Eratosthenes, and now we're even finding ways to make it even faster. What else do we have up our sleeves?
Well, there's actually one more optimization that we can talk about. This one's all about how we store information about the prime numbers in the sieve. It involves using a slightly different way to organize the data that can save us a ton of memory.
Ooh, a memory-saving optimization. I'm always up for that. Let's hear it. All right, so we've been talking about how to optimize the Sieve of Eratosthenes, and you mentioned a memory-saving trick. What is that all about?
Okay, so remember how we've been using that Boolean array, the ice prime array, to keep track of whether a number is prime or not?
Yeah, each element in that array, whether it's true or false, takes up some memory.
Right, and especially when we're working with a ton of numbers, that memory usage can really add up. So this optimization is all about using less memory.
Okay, I like the sound of that. How do we actually do that?
So instead of storing these Booleans, we can actually just store the odd prime numbers themselves.
Wait, hold on. How does that help us figure out if a number is prime? It seems like we'd be missing information about all the composite numbers.
Let me explain. So when we were using the Boolean array, we needed a spot for every single number up to n juror, right? But we already know that all even numbers except for 2 are composites. So we don't need to waste memory storing that information.
Okay, I see what you mean. By only storing the odd primes, we're basically cutting our memory usage in half right from the start.
Uh,
We can handle the case of 2 separately, but how do we actually check if a number is prime if we're only storing the odd primes?
we can use special data structures that are really good at checking if a number exists, like hash sets or bit sets. These are super efficient for that kind of thing. So whenever we find an odd number that's prime, we add it to our set. And then when we need to check if a number n is prime, we just see if it's in the set. If it's there, it's prime. If it's not, then we know it's composite.
So it's kind of a trade-off. We're using less memory,
Yeah.
but it might take a tiny bit longer to search through the set compared to just directly accessing an element in an array.
Yep, that's the trade-off. But a lot of times, saving memory is more important, especially when you have a huge amount of data. It's all about figuring out what works best for your situation.
This optimization really shows that there are many ways to solve a problem. And the best way depends on what you're trying to achieve. It's about understanding the trade-offs and making smart choices.
Absolutely. And that's what makes algorithm design so interesting. It's not just about memorizing solutions, it's about understanding the main ideas, thinking critically, and then using those ideas to find the most effective solution for each problem.
Well said. We've covered a lot of ground today. We started with a simple brute force approach, then explored the sieve of Eratosthenes, and even learned how to optimize both of them for speed and memory.
And we saw how understanding some basic math about prime numbers can help us create really efficient solutions. It's all about constantly trying to improve our code, even when we're dealing with these classic algorithms.
It's been a fascinating journey through the world of prime numbers and algorithms. Thanks for joining us on AI Codecast. We hope you've learned something new and are inspired to keep exploring the amazing world of coding.